Hi there, hopefully you're joining us in the third part of the op-amp series. In this video, we will be discussing active first-order low and high-pass filters. Low and high-pass filters are a result of combinations of circuit elements. Low-pass filters allow signals that have frequencies below the cutoff to pass while attenuating higher frequencies. High-pass filters do the opposite. Active filters are different from passive in that they utilize operational amplifiers to boost the signal being filtered. First, we will discuss active low-pass filters. Give me a quick second as I draw the filter. As you can see, the voltage input goes into the inverting input, so we have an inverting amplifier. Using the simple equivalence from the previous video, we can make Zi equal to Ri and Zf equal to the parallel combination of Rf and the capacitor 1 over j omega Cf. We can say that Vout divided by Vin is equal to negative Zf divided by Zi, which is equal to the parallel combination of Rf times 1 divided by j omega Cf divided by Rf plus 1 divided by j omega Cf divided by Ri, which is the input impedance. Rearranging the equation, we get negative Rf divided by Ri times 1 divided by 1 plus j omega Rf Cf. If you didn't quite follow that, pause the video and work out the math on your own. In a minute, you'll see how to do it for the next example. The voltage gain AV as a function of frequency for a first-order system is equal to AV0 times 1 divided by 1 plus j omega divided by omega C. This is the standard equation. Here we know that AV0 is equal to negative RF divided by Ri for the above circuit and is the DC gain. The value comes from the previously found Vout divided by Vin ratio. Omega C is the cutoff frequency, which is equal to 2 pi fc. This cutoff frequency can be found by extrapolating from the first-order transfer function that we just worked out. We take the second term in the denominator and set it equal to j omega divided by omega c. Solving, omega c is equal to 1 divided by Rf Cf. Taking this information, we can plot the gain against frequency for this low-pass circuit. The y-intercept should be AV0, and the point at which the slope changes is the cutoff frequency. The slope is negative 6 decibels per octave. Now we will look at an inverting active first-order high-pass filter. Again, we simplify the components into Zi and Zf. Zi, in this case, is the capacitor 1 divided by j omega Ci, while Zf is the parallel combination of Rf divided by Cf. This parallel combination is simplified in the same way as the previous problem, to ultimately get Rf divided by j omega Cf Rf plus 1. Here I'll show a little more detail. Multiplying by j omega Ci, we get negative Rf j omega Ci divided by 1 plus j omega Rf Cf. Vout divided by Vin as a function of frequency is equal to negative Zf divided by Zi, which is equal to the parallel combination of Rf divided by j omega Cf Rf plus 1. Divided by the input impedance, 1 divided by j omega Ci. Note the negative sign on the right side is just to show that the ratio is negative, not that the negative sign cancels the one on the left. We want to rearrange to get the first-order transfer function for an active high-pass filter, which is S divided by S plus omega C. We can do this by dividing the equation by RFCF to get negative Ci divided by Cf times j omega divided by j omega plus 1 divided by RFCF. We are now in the right format to be able to determine the gain and cutoff frequency. The gain, therefore, is negative Ci divided by Cf. The cutoff frequency is 1 divided by RFCF. Here is a brief representation plotted. The y-intercept is positive Ci divided by Cf, and the cutoff frequency is 1 divided by RFCF. If graphed against frequency, then the x-intercept would be 1 divided by 2 pi RFCF. Alrighty, I think that's it for now. You've got this.